Hello everybody, welcome to my channel. Today we have a very good problem for you guys called find peak element. Right? She's a very good problem, so make sure you pay close attention to the problem statement, right? So it says a peak element, right, is an element that is strictly greater than its neighbors, right? So given a zero index integer array nums, right, find a peak and return its index, right? So if the array contains multiple peaks, return the index to any of the peaks, right? Very interesting. Okay, so you may imagine that nums of -1 equal to nums of n equal to negative infinity, right? So what they're saying, guys, right? So in other words, an element is always considered to be strictly greater than a neighbor that is outside the array, right? So, okay, so what they're saying, guys, right? So for the first to last index, right, you might see that, they don't have, so for the first one, right, index, right, there's no left neighbor, right, so you can imagine that the neighbor that's to its left, right, is nums of -1, right, is equal to negative infinity, right, just like the right one, right, there's no right neighbor, so uh, we consider its right neighbor to be negative infinity, right? So that's kind of what they're saying here, right? So we must write the algorithm, right, that runs in O of log n, right? So very, very good thing that they've imposed such a tight complexity on us, right? But I think we'll manage, we'll be able to do it, right? So the problem statement is pretty simple. So find an element, right, that is greater than its neighbors, right? So, right, the neighbors, they're left and right neighbors pretty much, right? So the example's got clarify the ask, right? So we're given 1, 2, 3, 1, right? So we could easily see a peak, right? Peak is 3 because it's greater than its left and right neighbors, right? We return index 2 as the answer, right? It's kind of what they're asking for, right? Uh, so this one's gonna be fun, right? So we see that we have a bunch of numbers, right? And we can see we have multiple peaks, right? We have 2, that's a peak, right? We have 1, 2 is greater than 1, and 2 is greater than this one, right? So we have multiple peaks, so this one works out, right? Okay. So we just need to return any of them, right? We don't need to return all of them, just any of them, right? Will suffice. It'll be accepted pretty much, right? Okay, so yeah, pretty good problem. So also a very key and important thing for this problem, right? There are no adjacent duplicates, right? So we don't have to worry about handling those cases, right? Which makes the problem a lot simpler when we start coming up with the algorithm that we need to come up with, right? So what I'm going to do with you guys, we're going to brainstorm or, and start thinking about it in our whiteboard, right? And maybe we can come up with an efficient algorithm, right? That can, satisfy the requirement, right? That they've put on us, right? And yeah. So let's quickly go to the whiteboard real quick, right? So she's our whiteboard, guys, that we have. Um, so right now what we're going to do is to go through the different cases that we may see, right? And then by going through those cases, we'll be able to come up with the algorithm that we need, right? Right? So with first case, so one of the case that we can see, right, is the case where we have a bunch of numbers, right, that are strictly decreasing, right? And that way we have 5, 4. So let's say with peak, right? The peak is a number, right, that's greater than its left neighbor and its right neighbor, right? So for this example right now, 5 is greater than 4, right? But might say, all right, cool. Which one's the peak in this one, right? Which number that satisfy both that's greater than its left, right? So 4 is not greater than 5, not good. 3 is not greater than 4, right? 2 is not greater than 3. 1 is not greater than 2, right? So where is our peak, right? Our peak is going to be the first one, right? Because we've in the requirements, right? They said that the first index, right, its neighbor is negative infinity, guys, right? So you can kind of imagine, right, I want you guys to do a dotted line where, anything to its left, right, for the first element, right, is negative infinity, right, So 5 satisfies that requirement, right? It's greater than its left, negative infinity, and also greater than its right neighbor. So we do have that thing, right? It's good. So it's greater than 4. So it satisfied the definition for a peak, right? So we return that answer as the result, right? Another case that we may see, right? The numbers are strictly increasing, right? So we already know that negative infinity, right? Also, there's negative infinity here as well, right? But all right, so let's say for example, right? So 1 is greater than 2. No. 1 is less than 2, so that's not gonna work, right? 2 is less than 3. 3 is less than 4, right? So which one satisfy, right? So the peak, this one's the peak, guys, right? Because of the fact that I told you guys, right? So the thing uh to its right? The last number, the element to its right neighbor is going to be negative infinity, which means this is the one that satisfies the constraint, right? Which is it's greater than its left and right neighbor, right? So it's kind of what this is doing, right? Okay. And then we have this other case where we can see it. So this is the case where, all the numbers are increasing, right? And it ends up being the last index, right? So they structured it in a way so that we always find a peak, right? It exists, right, in the array, right? So that's why they say in the prompt statement that there's always a peak. So we don't have to worry about this case where there's no peak, right? So this one is another case where you can find it. It happens in the middle, right? So it increases at a portion of the array and then it starts dipping again at another portion, right? So this is what a peak is, right? She's actually the other problem that we did, right? Found mountain in an array, right? So I'll probably link it up so you guys could check it out. This one, it was a little bit more simple, easier to understand, right? So it's kind of problems, right? So it starts increasing and then it starts to dip, right? All right. So this problem is a little bit different because there may be multiple peaks, right? Which makes it, a lot more fun to deal with, right? So you see, this is the ideal case, right? We go up and then we end up dipping, and then that's our peak, right? At the, at that point that we see the dip at, right? And then we have this other case where we have multiple peaks, right? I just wanted to illustrate that so you guys can understand, right? So it goes up, right? And then goes down. That's a peak right there. We could return this one or we could return that one, right? Or 4, right? So either one is fine with a peak, right? Okay, so now that we've gotten those out the way, right? So how can we easily solve this, right? So the easy way, right? I'm thinking, right? We always like to start with the most brute force solution, right? Hopefully we can start, thinking and start, getting our brain going, right? I'm saying for this kind of problem. So what I'm thinking here is the brute force, right? Without trying to be, clever or anything like that, right? So we do a linear loop, right, through the array, going from left to right and checking it for every element, right? Our left and right neighbors, right? Are they, am I greater than my left and my right neighbor, right? So for each one, right? So first element we check, right? Am I greater than my left, right? Which is negative infinity, right? And then am I greater than my right, right? I am, then automatically I return it right away, right? Because it satisfies that constraint, right? That we have here, pretty simple. We do the same thing here. Is 1 greater than negative infinity? Yeah, I am. Is it greater than 2? No, it's not, right? Does it satisfy, right? And we do the same thing. 2 is not greater than 3, right? 3 is not greater than 4, right? We keep changing, and then we finally get to the last element, right? We know the right neighbor is negative infinity, right? And then it's greater than 3, so we return that right away, right? So pretty much that's how we would do, brute force, easy, nothing too sophisticated there, right? So now that we know that the time complexity that we're striving for is a log of n, right? We know that log of n and the algorithm of choice, right? When it comes to, be able to find like things in log of n complexity, right? We need to do some sort of amount of research, right? Pretty much discarding half of the array at every iteration, right? Really, really, really useful for really large data sets, right? Which is when it needs to be that efficient because they've already said it, right? It needs to be a log of n, right? So how can we use boundary research for this particular problem, right? It's kind of what we might be thinking. So to use boundary research here, I think we're going to need to pretty much, we know it's going to be, we're going to have to start with the middle element, right? And at the middle element, we need to ask a series of questions to know which part of the array we should get rid of, right? Right? So that's what we need to figure out, right? Right? To figure out the what definition, right? And then also, why do we discard that, right? So the way that is going to work, guys, right? So is that we're going to get the middle element, right? And we're going to compare it with our right, to our right neighbor, right? To kind of guide us in which direction we should focus our energy in searching, right? Okay. So for example, for this example, I start for example that we have here, right? So the middle element is mid, right? And then we check with our right neighbor, right? Am I greater than my right neighbor, right? If I'm greater than my right neighbor, then it means that I'm descending, right? And which is why that I'm not going to focus my energy going to the right. I'll focus my energy searching on this portion of the array, right? Including mid, right? So from the left up to mid, this is where my peak might be because, right? So mid is greater than its right neighbor, which tells me that mid might be a peak, right? And there must exist a peak on the left portion of the mid, right? And including mid, right? That's why we're going to focus our search space there, right? Because, all right, got to think about it a little bit, right? So what are the cases that may happen, right? So the cases, or let's say, we add all the numbers from left to mid, right? Going down, right? Up to mid, right? Right? Okay. Or, right, we had another point where, let's say, for example, we had another peak, right? So, so the worst case that we can have here, right? the mid does happens not to be the peak, right? But we just want to focus our energy there, right? And that partition, right? There's going to be at least one. There's going to be just guaranteed to be at least one peak there, right? So for example, right, five ends up being the peak in this particular thing, right? So after because we already know that, and I'm going to my neighbor to my right, right? So going to the right wouldn't help out because mid plus one is smaller than mid, right? So focus my energy on the left side, right? And so worst case we have all the numbers are in decreasing order, right? And if they're in decreasing order, then it means that the first element is the peak, right? Or it went something like, let's say we had a six here, right? Instead of a four, we had like six, right? It will still work out the same way. Six ends up being the peak, right? We went down, we went up and then down, right? Or it could have been the other case as well, right? Where we had a six here, right? Six, and we had five, right? Switch it, all right? It would be down, then up, right? And then it means that six would have been the peak as well, right? Because six is greater than its left and it's right? So whatever case it's handled, it's guaranteed to find one, right? Yeah. So hopefully that made sense to you guys. So let's quickly, all right, finish the how the things gonna work, right? So we do the binary search on that side, right? So binary search, we like, all right, cool. Is mid plus one, is mid plus one greater, right? If it's not greater, right, and mid is actually greater than mid plus one, then I focused my search base on that side, right? On the left side, right? Because including mid as well, right? So I focus my energy on the left portion and including mid, right? So I apply another binary search. I ask, is my left, right? Is my mid plus one greater? It's not greater. I'm actually greater. Then I reduce the search space once again, right? Which means focus on our energy there. Right? You see how guiding how using binary search and checking ourselves against our mid plus one, right? If mid plus one is smaller, then I don't need to go to my right because we're going downwards, guys, right? And it's not gonna help me finding a peak, right? Even though there may be other peaks littered in your array, it doesn't matter. I just want to find at least one of them, right? And I'm guaranteed to find that because of the reason I explained, right? Going to the cases. So let's do this one. I think this one's gonna help in seeing it a lot clearer. Right. So let's use this one real quickly. Okay. So for example, right, let's say we have so we apply binary search here, guys, right? Okay, we start from this one, right? So we ask is mid plus one greater, right? Yes, it is greater, right? So therefore, since it's greater, then mid plus one might be a peak, right? I know mid is not a peak for sure because mid is smaller than mid plus one, right? Right. So even though we see that there's a two nearby here that could have been a peak, right? But it's all right. We're allowed to miss it. We don't have to get all the peaks. We just need one of the peaks, guys, right? Which is enough, right? So now our search space is going to be from mid plus one onwards, right? To the right boundary, which happens to be the last element in the array, right? So we just go ahead in that part of the array, right? So we're guaranteed to find a peak here, right? Either mid plus one is the peak or some other number at the peak, right? So the worst case that we can have, right? Let's say instead of this one, we had a five, right? It kept increasing, right? It went to four, five. Four is not a peak, right? Because four would be less than five, right? And then in that case, five would be the peak, right? And we can't have cases where, for example, right, let's say the four, and we have another four, right? No, there are no adjacent duplicates, right? So it can't be something like four, and it wouldn't be a peak, right? But we can't have those cases. We don't have to worry about those cases, right? Because of the fact that there are no adjacent duplicates, right? So yeah, it looks good so far, right? So either we have four or we end up dipping again, which is the case that we have here, right? So it goes up, right? And like the last element is the peak, or it finds a dip, right? And then that's the peak, right? So we're guaranteed to find it because of those cases that I've told you, right? So hopefully it makes sense to you guys. So let's quickly go into the code. I think it'll make even more sense to you guys, right? So yeah, so we've come up with the algorithm, right? So now all that's left is to pretty much write it, right? So we start with the left and right corners, right? Minus one. And then what we're going to do is the while loop. While the left is less than the right, we're going to calculate our midpoint here, right? This is a very standard way of calculating it. So now we're gonna ask those two questions, guys, right? If nums of mid, right, is less than nums of mid plus one, right, to its right neighbor, right? So if nums of mid plus one is greater than I am, right, then mid plus one might be a peak. So I'm gonna focus my energy and guide it and go into the right? So search for your peak on there, right? Like we said, right, we don't need to find all the peaks, right? And we're guaranteed to find a peak in that from mid plus one and onwards, right? To the right boundary because of the fact that I told you guys about the different cases we may have, right? Either we're all increasing, right, and there's no dip, and the last element ends up being the peak, right? Or there's it starts to decrease, right? And if it's that case, then the mid plus one will be the all right. Or there's a there's a peak in the middle, right? And we're guaranteed, right? So I just want to make sure that it makes sense to you guys, right? So in this other case, right, let's say mid plus one, mid is greater than mid plus one, right? There are no adjacent duplicates, right? Like I said, right? So mid is greater then mid plus one, right? Then we guide our search page. We go to the left, right? From the left boundary to the right, to mid, right? That's where a peak might exist, right? And we're guaranteed to find that one, right? Just like I've explained in the walkthrough. So hopefully it made sense to you guys, right? You know what I'm saying? Let's press run. No, I'm tripping. I meant to turn to the left. That made no sense at all. All right, looks good. Let's press submit. Awesome, guys. We're able to pass all the test cases. So if you guys found value, guys, to the thought process, you guys enjoyed it, in the comment section, if you're new here, make sure to subscribe because we'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.